Hello. Now we are going to introduce another machine type called non-deterministic finite state automaton, or NFA. What you will see is that non-deterministic finite automata, or NFA, help you specify languages needing far fewer states. Eventually, we'll of course use another notation called regular expressions that directly convert to NFA. And so you'll have a textual form for NFA, which will be even more convenient. But before that, at least let's enjoy the intermediate amount of luxury afforded by NFA by not having as many states as a DFA and mentioning things compactly. Also, the notion of non-determinism is important in computer science. It arises in several areas. It is a foundational discovery that computer scientists made. And when it comes to non-deterministic Turing machines, you'll be able to understand why computational complexity, which is the amount of time that a program takes to run, can be modeled with or without non-determinism. And their non-deterministic Turing machines arise, and that needs to be understood carefully. So it is very important to understand NFA, non-deterministic finite state automata, well before we launch into other non-deterministic devices. So that's where we are now. We are going to illustrate NFA using the same language, which is the second last or third last is one language. So let us start by running a suitable notebook for it. And once we load the definitions in this notebook, we are going to load up the first simple NFA. And I have coded up the NFA already, but let me tell you how you might code it again without influencing your understanding by a preset example. So suppose I define third last is one, TRD, last one, NFA. You can see what the language is going to be. Anything that ends with not the last, but not the second last, the third last should be a one. So the essential property of an NFA is you still define the state machines starting off with the keyword NFA and all that, but states can have multiple transitions from one state to the other. States can also go to another state without seeing an input symbol. So you can actually move on the epsilon string, not just a symbol that a DFA needed each time. So that notion exists in NFA, and we can use it to create two different illustrations. But before that, the basic state structure is going to be an initial state where you may want to stay on a 0 or a 1, just like that. And the purpose of this idea would be very clear very soon. But let us draw it. As we draw, it'll become clear what the device is going to be. So you can see that I'm creating a machine that just goes back to the I or a 0 or a 1. That may confuse you because in a DFA, no more moves are permitted from that state on any of the symbols 0 or a 1. But in an NFA, thankfully, you can create additional moves. And the additional moves that we are going to create are going to be the relevant moves of the NFA when it sees the magic 1. And let us say that it leads to a state called S1, which just says that from the state I, we might be seeing a 0 or a 1 any number of times But you may, when you see a 1, you can go back to I or to S1. So the machine splits into 2 with state S1 modeling the fact that we have received a 1. Now what do we do? We have seen the one that we are interested in. So the thought process in designing an NFA is simply move on any symbol in this example, call it S2, perhaps, because the state letter doesn't have too much of a significance as to whether it's a 0 or a 1. So just go to S2 and one more symbol later. We are ready to accept the string so far. So what an NFA does in this example is to keep the symbols of relevance and then followed by the don't cares, and not bother to specify every move in every case, like there is nothing specified out of F, and also allow 2 different moves out of state I. All right, so this is one way. So let's look at another coding. Okay, so we could also move through an epsilon move or empty string move. So this would be another version which I had already coded up. And here what we see is we allow the machine to move on a 0 or a 1 on state I, but allow the machine to read nothing or an epsilon and come to state as 0. So then we situate the magic 1, which is the third last after a 0. That also is equivalent. And the way we see that is by simulating the machine that we need to, NFA ends in 0101 is another machine. So we'll do an interactive simulation of 2 NFAs here, one being the N1 NFA and the other being the N2 NFA, and we can feed the machines. Okay, so third last or 0101 can be fed. So just to code yet another example by using an NFA. Any string that ends in 0101 can be captured simply by spelling out the pattern of interest like 0101 and then letting the machine stay in the I state. Okay, so now we are going to show both machines running. So we're going to create a widget and feed either of these machines. NFA ends in 0101 or third last. Okay, so let's run this code cell and so run the test string. So let's run give the 0101 and 1, let us say. Okay, so maybe 010. So this is third last. Okay, so now we had to specify which machine we are running. So we give this one. And let us say that the machine that we are simulating is third last. So when you give third last, the string so far, it has not seen enough symbols, so it cannot accept. So let's give one more and run it again. And now we can see that the machine has gone into state F also. So the general idea is that suppose I bring third last machine to the initial empty string. I'm actually controlling the length of the string that I'm feeding. I give it 1 symbol here. So it has reached the state I and S0. Okay, I and S0. This is the third last that we are simulating. Give it one more symbol. Then it has reached I, S0, and S1. So you can see that the machine splits into 2 copies. The copy that reached S0 is marching over this 1 to go to S1 also. Now, if I give it one more, strictly one more, then it has reached S2 because the third symbol doesn't matter. But so the machine is in configurations I, S1, and S2. And if I give it one more, which is the full string, now you see the machine has reached F. So this is the third last. So suppose I add one more 0. Then there is no third last, and we'll have to slide the slider one more. And you can see that the machine that was in state I, S0, and F has now simply attained state I, S0 because the token that was in state F has fallen out, so to speak. And now this doesn't have satisfy 0101, so none of that would be accepted. So let's go there. So if I go all the way here, I can feed as 0 and 1. So 0, 1, 0 even. So it has gone to S0, S01, and S010. And since there is nothing more, it has reverted to IS0. But suppose I were to change this to 01010, let us say, and let us try one more. So 010, and how much have we fed? So we just need to feed up to 0, 1, 0, and let's feed one more. Okay, so now it has attained the state IFS01, IFS01, which is indicative of the presence of token in 3 states. But since it includes one of the final states, the string is deemed to have been accepted. That's the acceptance of an NFA if one of the split machines accepts. Okay, so now these can be animated also. So let us draw an create an animation, since the animation widget animation facility exists. So if we want to bring the animation facility from one of the earlier machines that we may have created, that works okay. So let us go to for CS3100 and overview. You can always grab the animation items from here and then change the animation to an NFA animation. So let's just grab animate DFA and then change it. Okay, so you can get it from other notebooks also, but I just got it from here. So now I am going to import from animate NFA, import star, and then call animate NFA. And then I'm going to give it the NFA that I want to animate, which could be either N010 or third last is 1, like that. Okay, so let's type that. Third. Okay, it already gives a completion. Third last is 1. Few just says false. Fine, that is fine for now. And then there is a display mechanism for loading font awesome. So at this point, third last is 1 is it's not taking that third last as a decimal literal. So something happened in terms of the naming. So NFA ends in 0101. This is called NFA third last. NFA third last 1. Okay, so that's the name, NFA third last 1. Okay, so okay, so let's give this a go and animate third last 1, and something else happened. So the display HTML got truncated. Let us make sure that it is not truncated. Okay, so display HTML. I think we'll use one more closing parent. Okay, so let's see whether that is the thing. Yes, indeed. So now you can see the 0 and 1 separately. Now let us try 0, 1, 0, 1, and let us do animate. Okay, so now it actually helps understand by stepping the machine. So if I single step the machine, you can see that it took the 0 transition through the 0 loop here. And now if I give it one more, it actually takes the empty string and it'll come and occupy two different states. So having seen a 0, the machine is in two different states already. And this is a free move without reading any symbols. So now if I step once more, it attains the state I as 0 as 1, having read 0 and a 1. After seeing a 0 and seeing a 1, you can trace out the trajectory. 0, 1 has a path here. 0, 1 has a path here because 0 epsilon 1 is 0, 1. So that's another way to look at the number of paths that are able to accommodate the string seen so far is 2 in this case. But it also has a presence in S0, because if it has a presence in I, then without reading anything, it also has the NFA also has a presence in S0. So this will help us introduce the notion of E closure or epsilon closure, which is the fact that if the machine is in a certain state, without reading any input, the machine can occupy other states also. So moving along, if I click 0, 1, 0, 0, 1, 0, 0, 1, 0 can remain here. 0, 1, 0, since it remains here, there is an occupancy here. 0, 1, and a 0 through this path. So if you go back, you can actually see that it took the 0 transition. So here, having fuse edges not present allows you to see which exact edge it is taking. Then we can take one more step and see where the machine ends up. And when we do that, we see that the occupancy in state S2 is now going to transition through 1. So having seen one more 1, the machine is going to occupy the state I S0, S1, F. So this is 0, 1, 0, 1, straight here, 0, 1, 0, and a 1. That can be here. And whenever you are here, there is an epsilon closure, which will bring you here. But there is also 0, 1, 0, and a 1. So the machine has accepted these inputs seen so far. So you can actually see that the NFA can accept through being in multiple states at the same time. And of course, you can do a fast simulation to confirm the behavior for other strings. So I'm going to feed a long string and see how the NFA moves through sets of states. And you can see that the occupancy of the NFA, this set of states that the NFA is in, goes through various subsets. But finally, since the third last is not a 1 here, the final ending configuration IS0, since it doesn't include a final state, leaves the NFA hanging in I and S0, and that is not an accepting state. So at this point, this machine has rejected that particular input. Similarly, you can change this one to third last is 1 and see the behavior. So I hope you see the power of non-deterministic machines and NFA in describing the language to be accepted without spelling out every possible move and every possible state. So these ideas will help you understand the notion of subset construction that is coming later, which are the subsets of NFA states that can be attained after seeing a specific chunk of the input. So now there are some notes on the design of the NFA. So I do repeat the third last machine, and we can actually convert the machine to a DFA, which is the algorithm that we'll be studying, or we can use the third last is 1 DFA and see the size of the machine. This is a repeat from the previous notebook, where we now see that the machine takes up an exponential number of states. So the fact that an NFA is a more compact machine becomes clear, and it becomes exponentially succinct in some cases. All right, so we have the same machine and repetition of the animation coming here. Okay, and what other operations can we do for on NFA? So that depends on what an NFA is and what all you would like to subject the NFA to in terms of stepping or running. So NFAs are structures which have a set of states, an alphabet, and notice that the alphabet cannot include epsilon in any case. The moves of an NFA being allowed on an epsilon is just an extra feature of the delta function, the transition function or transition relation. But also the NFA are allowed to start in multiple start states. So the set of start states is a subset of the set of states. This is a deviation from many books, which always, most books allow only a single starting state, but except Dexter Cozen's book allows multiple starting states. And the reason to allow multiple starting states is quite simple, because it is more natural to allow even the starting state to be picked not deterministically. And also, there is another algorithm called Brzezowski's algorithm, where we can minimize DFA by turning by a sequence of constructions such as reversing DFA to get an NFA and determinizing it and doing those steps again. So Brzezowski's minimization can produce the same number of minimal states of a DFA, provided you make the NFAs not have arbitrary initial single states being forced. Many books allow you to have a single starting state, and then if you really want to be in two different states, they force you to branch out using two epsilons, but that is an extra state hanging around. Instead of that, you can have two distinct start states. So we can actually see that design very easily. Okay, so let us see whether this is a machine like that. Probably not. This is also not a machine which has multiple start states. This is a machine that branches out on an epsilon to two different states. And this is the artificial initial state that I mentioned that you can dispense with. Instead, you can allow the NFA to start from A and G separately. And that is the attempt that I'm going to show you here. And now you can see that this NFA can start with IA and IG, from IA and IG. And that allows you to dispense with this arbitrary initial state. That's much more economical, and most scholars agree that this is the way to proceed, even though many books today for convenience simplify the NFA construction. But anytime you go into more elaborate algorithms like Brzezowski's minimization, the presence of the extra states starts hurting. It doesn't give the same minimal DFA state count. Okay, so this is the machine with two initial states, and we can see the state structure. And you can indeed see that the starting set of states, Q naught, is IA and IG. So it is a set of states where you can start the NFA from, which is what I'm also using, much like Dexter Cozen's book. And now we can animate such a machine, and let us see what happens. So if I give it 0, 1, 0, 1, I don't know what the language of this machine is, but we can find out by animating. And after, so the machine is already initialized in state IA and IG, you can see that. And after a single step, the only surviving machine state is after IA, there is an epsilon closure, which is a move on epsilon. And that 0 has brought the machine to state E. And as soon as you perform the move on a 0, you can close on epsilon. So this epsilon closest to IA, this epsilon closest to IG, that will become apparent. So without consuming anything other than a single 0, you are going to be in multiple states. So state C upon a 0 put you in E. But as soon as you are in E, you are in IA and B and IG and E itself. And the reason that you are back to C is because there's an epsilon path here and here. So it is as if you reach state E and you put a high voltage wire over here and treat all the epsilons as freely conducting paths with a diode, one-way diode. So that diode will conduct the high voltage to here, 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 and here. So you can get shocked if you touch any of these states. And that is a good way to think of the epsilon closure of a state. If you put a high voltage on E, you will get zapped if you touch E, but you will also get zapped if you touch any of these states. And that is the epsilon closure of a state. And this is a very graphic way to teach epsilon closures that I find. So you can actually finish stepping through and see whether this string gets accepted. That is the rest of the detail. And after 0101, indeed, it has become an accepting configuration because now you have a presence in all but one state. But more importantly, you are including a presence in state F. So that would be an accepting run for this machine for 0101 also. Now that I mentioned that NFA can be converted to a DFA, let us see how that is done. So third last is one NFA has not been defined. So we may have to run that and come back. Where I don't know where that was. Otherwise, we'll define it. I guess I didn't run this cell. So let us see whether that run helps us finish the constructions in this notebook. So coming here, what you see is third last is one NFA is not defined. Third last is one NFA. So let us make sure that is defined. Otherwise, we'll give it a different name. NFA third last is one. That name exists, so we could give that. But let us see whether the other machine third last is one NFA alt. Oh, okay, that's how I typed its name. Oh, this one has not been run. There is a third last is one NFA over here. So at this point, we should be able to hopefully finish the animation, the execution of the. Okay, so here you go. So this is the third last is one NFA that we're going to convert to a DFA. So this is the NFA to DFA, which converts this NFA to a DFA. And you can actually see that the number of states has blown up. In here, you had this many states. Here, you blew it up to 8. And you can actually draw the machine. And this is the NFA that converts to this DFA. So the algorithm itself has to be studied next. And that's where we'll be going. And we have some more material to go through. So I hope this is a good point to end this notebook. So to summarize, NFA are devices where the finite state structure is compact and it only models relevant transitions. It allows multiple initial states. It allows the same symbol to take you to 2 different states. It allows you to move on in epsilon. And you can see that the acceptance criterion is when an NFA has reached multiple states where one of them is a final state. And finally, you can convert NFA to DFA. And sometimes it incurs an exponential blow up. So thank you. And hope you can practice this material. And we'll come back to more as time permits. Hope to see you soon.